And alrighty, so the way I'm going to be doing this is I figure I'll give you guys about a minute or two if you want to try taking on the question. And if you want, you can go ahead and also type your answer in the chat if you want to do that. Or if you guys just want to go through, have me go through the question, just let me know also in the chat. But here's question number one. So in AP Classroom, you will see that I have assigned a Mechanics 1 review. And so that's what this assignment is. It's not necessarily an assignment to do, but if you want to follow along on the questions in AP Classroom, you'll be able to see them there. That way you don't just have to try to squint from via Zoom, which I think may not always lend itself to the most visibility. But let me know if you guys would like to take some time to sign into AP Classroom and that way you can see the questions. And then I'm just going to test here, make sure that I can see everything. Okay, looks like pen's working. Sorry, it turned out Zoom signed me out of my home computer and it wasn't detecting anything. So I had to kind of hobble together a setup here with my laptop, but it's working. Okay. So let's see here. Does the Zoom work? No, we're gonna have to zoom in over here. Okay. All right. So this question reads, the acceleration due to gravity, oops, there we go, on the moon is given by GM. And some of these questions may be familiar. Maybe some of these have been assigned in previous assignments. So if they ring a bell, that's great. Hopefully you, more than anything, remember how to solve them as opposed to maybe you recognize the answer. But either way, let's go ahead. And so we're going to drop an object from the moon at a time, from a height h. The time it would take the object to reach the moon's surface would be Tm. The object is dropped from the same height on Earth, where the acceleration due to gravity is going to be g of e. The time it takes the object to reach the Earth's surface is called TE. And what they want us to answer is, which of the following is the correct mathematical relationship between the two times, the time that it takes it to fall on Earth versus the time it takes it to fall on the moon. And so maybe I'll give you guys about maybe a minute or so. Turn on the touch features. Okay, so it does work on the tablet, just may not be as efficient. Okay, so let's go ahead and start looking at this. Well, the first thing we know is that they're being released from the same height. And so there's a couple of ways to approach this. If we release an object from rest, we kind of have that shortcut where the time it takes an object to fall is given by square root of 2 times the height, if you will. Ooh, I need to get used to writing with this. Going to be 2 times the height over g, all of that square rooted. And so we can go ahead and make a ratio out of this. And we can go ahead and compare the two ratios. Now, what I think actually might be a little faster here in this problem is recognizing that because we have the same height, the displacement's going to be the same. And so when it's released from rest, like delta y or h is given by 1/2 at squared. That's actually how we solve for t for this problem, if we wanted to actually find the time. But because they have the same heights, we're going to go ahead and set two versions of this equation equal to each other. 1/2 g of e times the time of e, which is the time it takes it to fall on Earth squared, equals 1/2 g of m times t of m quantity squared. Okay, so we could have even started with a proportion and just realized that delta y is proportional to t squared. That's really, I think, the quick way to answer this question. Oops. I'm going to turn off the touch features. Okay, so the halves cancel because they're constants. And so we're going to try to solve for the time it takes it to fall on Earth, because all our answer choices are like that. So at the end of the day, the time it takes it to fall on Earth is going to be given by the square root of gm over g Earth times time squared. And then we could be like, oh, we got to square root all that. And that may not look necessarily like the answer there. But if we recognize that we can split this as the product of two square roots, the product here remains, but then the square root of t squared cancels, and we just get t of m, which is going to give us this one here. Recognizing the proportionality of t squared, at the end, you're going to have to solve for t. You should have hopefully recognized, oh, I should have at least one of the first two answers. And then you actually don't even have to do all this work. We can even kind of rationalize it or make reason of it. We have the square root as expected by solving for t, but then we should expect the time on Earth to take less than the time it would take it to fall on the moon, right? Because Earth's gravitational field is greater, it should do it in less time. So we could recognize, okay, which of these two, this is going to give me a fraction that says less. So B, bam, let's go. All right, next one. So here we have some dots. And I don't know, I do think that these are familiar. So again, if you guys want me to jump ahead to the newer questions, let me know. But we've seen one of these motion maps, if you will. Don't want to erase this. Oh, well, I'll clean it up for formatting later. But here are the dots. Starting from rest, a car moves to the right in a straight line along a track. The motion of the car represented by the dots is shown, recorded at equal time intervals. Which of the following best represents the acceleration vectors at the beginning, middle, and end of the motion? So I'll give you guys some time to think about that. Pull up the chat. Okay, nothing in the chat. All right, as expected. No, not the nothing in the chat. I was like, I was looking at the answer. So, so more than anything, I was expecting the certain answer. Okay, so let's go ahead and see here. So it looks to me like if it starts from rest, okay, move some distance. It looks like it's gained some velocity. Hey, look, it got faster. So it looks to me like because it's getting faster, the acceleration is in the direction of motion. So automatically, oh well, D has it in the correct direction, so we'll kind of keep it, but we'll have to make a comparison later. Okay. My goodness. There we go. And then afterwards in the motion, we notice, okay, well, the spacing of the dots in this interval here in the middle, this was constant velocity. That is so poorly written. So we should expect zero acceleration. So automatically, well, bam, there's our answer choice. Very good. Now that I think about it, I feel like we did these questions in one of our games in class. Yeah, these questions look very familiar. Let's, I think we even did this one.
We did do these.
We did do these a while ago. Do you still want to go through them or you want to jump to newer questions?
I guess newer questions.
Newer questions. All right, we'll jump because I think like the first 19 or so are going to be familiar. And I don't think we're going to get much out of that if that's the case. So yeah, these look really familiar actually. There's a free response because I never like look before I print. So there's a couple questions. 18 and then 19. Oh, you know what? Here's a classic problem. Now that we've kind of really gone through the course, I want to see what we think about 19. So it reads, a particle moves in the xy plane with the coordinates given by this expression for the x component and the y component. And they give us the amplitude of oscillation, if you will, or the amplitude of the maximum amplitude. So at most it's going to be 1.5 meters. And then at a frequency of 2 radians per second, or we can think of it as the angular velocity of 2 radians per second. The question is, what is the magnitude of the particle's acceleration here? Oh man, I need to redo a paper. Oh, wow. Welcome, welcome. And so and I'm going to try not to call y'all by name since I'm putting these on the internet, right? But for the individuals that just joined us, I've gone ahead and made a set of questions on AP Classroom. They are called Mech Unit 1 Review. And if you want to follow along on AP Classroom, you're more than welcome to. And I recommend it because I don't know if the screen share on Zoom is, like visible or like really good to read.
All right. Thank you, sir.
Mhm. So we may be wondering, well, how are we going to answer this question? Well, if we remember, somewhere along the lines, we had an expression something like a omega squared, and maybe that sounds familiar. And so let's go ahead and see how we're going to do that. Well, it doesn't matter which equation we look at here, because the quick way to get the acceleration is to take the derivative of this and not really even worry about the negatives. Yes, when we differentiate cosine and sine, we're going to get a series of negatives in there, but ultimately we're looking for the magnitude of the acceleration. So at the end of the day, when I differentiate these, I'm not going to stress over the negatives. But just be mindful that if you're actually doing a calculation where you need the direction, you should. So we have the position. So by now we've seen that the rate of change, or the instantaneous rate of change of position with respect to time, or the derivative, is going to give us the velocity. And then if we take the derivative of velocity with respect to time, that's going to give us the acceleration. So the end game is we need to take two derivatives of this function, or we need to differentiate this function 2 times over so that we can get an expression for our acceleration. So this becomes, like d dt of a times cosine of omega t. Yeah, let's put parentheses. So the good thing is the amplitude here doesn't change with time. So we could take it out of the derivative term, and recognize that we're really going to be differentiating cosine of omega t. And so this comes out to be a sine of omega t. But then we got to remember that here we have a function within another variable. So we're going to have to do that chain rule where we take the derivative of the outer function, which was cosine, and which yields sine, but then we need to multiply by the derivative of the inside, which is omega. And so if we wanted to get the velocity as a function of time, and as a magnitude, we would just say it's a omega. That would be the maximum velocity. So to get the acceleration, we differentiate this once more over, and the same.
Sir,
uh-huh.
Isn't the derivative of cosine negative sign?
Yeah.
Or-
But I'm saying, like, I'm not worrying about the negative. But we'll go ahead and put it in there. Okay. So yes, very important. So you know what, just to kind of keep it consistent and like for future reference, I'll go ahead and put those negatives just so that like as we review, we do recognize that. Okay. So when we take the derivative of this again, we're going to take the derivative of sine. I'm going to pull out the negative a d dt of sine of omega t. And we're going to get the same thing again. And so this becomes a omega, sorry. So then this becomes a times omega times cosine of omega t times omega. And that's going to give us our acceleration. Oops. I need to put in the hotkeys on this tablet so that I can be a little faster. Oops, exactly like there, changing from eraser to pen. Our acceleration as a function of time. Okay. So recognizing that we have two omegas, here we go. So a max, which one is the undo? And scroll, nope, I don't have it. So at the end, A happens to be 1.5 meters. Omega is 2 radians per second. And radians are units, but they're not really units. They're really the ratio of like length to radius, which are both going to have the same units. And so those units cancel out meters per meter in its definition. but we usually put it there just so that we understand in what like angle measurement we're working with. So at the end, this is 1.5 times 4, which is 6. So there's that one. Hopefully, even though this is an older question, we were still able to get a really important application here that starts to bring in like harmonic motion or rotational motion and non-constant accelerations where we got to take some derivatives and integrals. So that was 19. Let's go ahead and see a newer question here. So some of these questions here may require parts of other topics, especially since we kind of already done all the unit specific questions. Some of the majority of these questions will still have or will call in units like mechanics or momentum or energy, sorry, mechanics, dynamics. So maybe this is one of those because it looks to me like we're dealing with a pulley, essentially an Atwood machine, but we'll see. So, and let me make sure this is not a free response. Rip, that it is a free response. You know what? Let's do a free response. Or do you guys want to do multiple choice? Because I was going to do one day multiple choice, one day free response. But we'll just do it live.
I think we should stick to multiple choice.
Okay, all right.
For today.
For today. All righty. All righty, here we go. So an ant of mass M clings to the rim of a flywheel of radius r, as shown above. The flywheel rotates clockwise on a horizontal shaft S with a constant angular velocity omega. As the wheel rotates, the ant revolves past the stationary points 1, 2, and 3. And the ant can adhere to the wheel with a force much greater than its own weight. It will be most difficult for the ant to adhere to the wheel as it revolves past which of the 4 points here? And so this question has been asked in different ways. They like to put ants on wheels, whether they're turntables or their plane is in the vertical direction. And so, yeah, this is more of a mechanics question here, or dynamics, sorry. But at the end of the day on the test, they're going to be kind of all jumbled up anyways. So a little bit of randomness here is okay. All right. So this question is asking, when is the force from the ant going to be the greatest? And we're just going to call its grip force like F ant, the force of the ant. So this is the ultimate question we are trying to answer. Well, let's go ahead and draw some free body diagrams. So when the ant is in position 1, do you think it has to grip onto the wheel a whole lot? Probably not really, because it just has to sit on it at that point. It just needs to stand on it, and it doesn't have to try to stay on the wheel because its weight is going to press it into the wheel here. But if we wanted to, we have on position 1, we have the normal force from the wheel. We have the weight of the ant. Oops. I'm going to write it as W to save myself a little bit of writing. I was going to do mg, but then I changed my mind. So we have the weight of the ant. And if things are nice and easy, the ant doesn't even need to grip the wheel because the normal force is going to be equal to the weight of the ant. Let's go ahead and look at position 2. Position 2 looks to be a little bit below the midpoint of the wheel, but I'm going to assume that they essentially meant the midpoint. Let's go ahead and look at the forces there. So when the ant is on that point, its weight, oops, I did it again. Its weight is pulling straight down. And let's go ahead and assume, well, actually we'll spare ourselves the assumption because it doesn't actually quite make sense if the force from the ant, its grip, is perfectly this way, because we're going to need some component of its weight or of its force to be vertical to balance out the weight, okay? But by and large, it could be essentially horizontal. Okay, so in this case, Oh my goodness. Sorry, I am still trying to get calibrated to this tablet because I haven't used it in a long time. So in this case, the force from the ant is going to have to be part centripetal and part of the weight. But if we notice, in this case, that this force here, this is going to be mv squared over r, or this component is mv squared over r, because that's the centripetal force, the part that points towards the center, which is actually, sorry, if we actually look at it, I drew this wrong. The component that is the centripetal force is going to be straight pointing this way, which is essentially the force from the ant, because its arms are behaving like a tensioner, like a rope. So this part right here is already mv squared. And then this is mg. Now, by the time we get to this, what we notice is that at this point, all of this part right here, F ant, and this is mg, we have F ant minus mg, and that has to be equal to mv squared over r. So what we find out is that the force from the ant is going to be not just mv squared over r, but also mg plus mg. Here we get a component of the ant's weight acting against it. The true weight of the ant is acting down. But as we've seen, we have components in this coordinate, kind of like if you want to visualize like a pendulum or a slide, we've talked about how we have components of our weight acting along the curvature of the surface or the incline. And when that happens, this right here, this is the component pointing away from the center. And whatever angle this is from here to here, that's going to be the angle right between these two lines. So that makes this guy mg cosine theta. So at the end of the day, if we do it in this frame of reference for the ant, this is looking really messy. We get that it's the force from the ant minus mg cosine theta equals, and let's scooch this over a little bit, mv squared over r. So it is a little hard for the ant to hold on at region 2, but if we look at how this function is going to behave, oops, I meant to put mg cosine theta. When is theta going to be 0 here? Well, theta would be 0 when the ant is at position 3. Well, what's cosine of 0? Cosine of 0 is 1. So we get a full count of the weight when we have to, when the ant has to hold on to its, not just its weight, but also the centripetal part, the v squared over r. And so in this case, while it's anywhere at an angle relative to position 3, it's only getting a component of its weight acting against the centripetal direction, if you will. And it's not until it's at position 3 where all of its weight is acting against the centripetal direction. Remember that this is the minimum force necessary just to move around in a circle. But when your weight is acting against you in these directions, you have to provide a force, not just the amount necessary to move in a circle, but also your weight. So putting this all together, 0.4 would be when it's perfectly horizontal from the looks of it. And when it's perfectly horizontal at position 4, the angle here is going to be 90 because it's 90 degrees from here to here. And so cosine of 90 is 0. So this is why I was saying that when it's at the perfect like side position, you don't really have to worry about the weight. The force is just mv squared over r. But position 2 does look like it's a little bit below that. So we are going to get a component of that weight mg cosine theta. So putting it all together, when would it be most difficult for the ant to adhere? Well, I think we could have answered this question hopefully by just looking at it. But think about this, like you're like on the outside of a hamster wheel, and to stick to the wheel, you don't really need to stick to it on the top because you're already on it, your weight's pressing you into it. But as you start to go over, you're going to have to grab onto the wheel to stay with it. And so when you're adhering to the wheel or you're grabbing onto it, it's going to be hardest at position 3.
I got you now. I misunderstood the question.
Okay, no problem. All righty. So sorry if that looked like a long explanation, but I wanted also to be able to back it up with the math. Okay, so let's go ahead and see here. Ooh. So here's graph interpretation. We notice that it's a sinusoid. We should be thinking, okay, this is some type of harmonic motion. And thankfully, the question does talk about velocity. So totally applicable for unit 1. An unstretched ideal spring hangs vertically from a fixed support. A 0.4 kilogram object is attached to the lower end of the spring, and the object is pulled down a distance of 0.35 meters below the unstretched position and released at a time of t equals 0. A graph of the subsequent vertical position y of the lower end of the spring as a function of time is given above, where y equals 0 when the spring was initially unstretched. And the question is, at which of the following times is the upward velocity the greatest? So I'll give you guys a minute. I'm sorry, I'm trying to be able to fit it all. Okay, so there's the graph and the answer choices. When is the upward speed the greatest? Or sorry, upward velocity. We are talking about direction, so we should be specific there. Okay, so let's go ahead and look at this one. Well, as we were talking about earlier, velocity is the derivative or the rate of change of position with respect to time. So we should be thinking, when is the derivative the greatest, but not just any derivative, upward. So it looks to me like as we pull it down, we have a negative direction for the displacement. So they're telling us down is negative. So that tells us when do we have the largest positive slope? Derivative is just a fancy word for the slope. Where is the slope the steepest positively? Let's go right here. So 0 seconds, nope. 0.25 looks pretty good. 0.5 seconds, no, the velocity is 0 at that point. 0.75 sounds good, but it's negative. So not this one. And then 1 second again, it is 0. Well, bam. Again, also this one still feels a little familiar. Maybe we've just done everything the College Board has to offer. No, I doubt it. Okay. Let's go ahead and see this one here. So we're given the velocity in the horizontal direction from the looks of it, or at least in the x direction, as a function of time. A car moves in a straight line along the x-axis. The velocity of car Vx as a function of time is shown in the graph above. The position x of the car at t equals 0 is x equals 0. And they want us to find out what is the average acceleration of the car during the interval from 0 to 10 seconds. So let's see here what you guys got. Oops, and just so that we know what kind of graph this is, velocity. Okay, we're going to go ahead and call it time there. So let's go ahead and see here. So here they're asking for average acceleration. Now there's a couple of ways to do this. We can get all of the average slopes, but we would have to remember that because the slopes are not constant, we would have to weigh these averages, which can get really time consuming and difficult because we can make a lot of mistakes with a lot of calculations. So the other thing we need to remember is that because acceleration is the slope of velocity, we want to find the average slope. So we want the average slope from 0 to 10 seconds. So let's go ahead and get the velocity at 10 seconds minus the velocity at 0 seconds all over the time at 10 seconds minus the time at 0 seconds. Wowzers. This becomes the velocity at 10 is 2 minus, and I'm going to ignore the units here for now, 6 all over 10. And so this becomes -4 over 10 or negative 0.4 meters per second or negative 0.4 meters per second squared. So it looks to me like B is our best answer choice. All righty. The next one deals with torque, well, not torque, but let's go ahead and take a look at this one here. Let's see if what you guys can do. A wheel with a rotational inertia I is mounted on a fixed frictionless axle. The angular speed omega of the wheel is increased from 0 to some final angular velocity in a time interval of t. And the question is, what is the average net torque on the wheel during this time interval? So unit 1 is kinematics. Now, generally, it's associated with 1D kinematics. I mean, not 1D, well, XY kinematics, not rotational kinematics, linear kinematics. There you go. But a lot of the principles still apply in rotational. So we'll go ahead and take, that's why I think we should do this one, is because at the end of the day, we could change all these to the linear versions, and we should be able to do that. Okay. So hopefully you've thought about it, and maybe this is what you were thinking. Well, we need to find the net torque. Net torque is a lot like net force. So we'll just go ahead and start doing two versions of this, net force and net torque, just so that we can see how we would do this for the linear version. Well, we know that the net force is equal to m times a, and the net torque is equal to the rotational version of mass, which is rotational inertia, times the rotational analog of acceleration, angular acceleration. Okay, all righty. And we may be wondering, well, okay, well, we have I, but then what do we got to do? We got to work with this term, the angular acceleration. Well, all accelerations, angular or not, are the rate of change of velocity. So in this case, this is going to be the change in angular velocity over the change in time. And we kind of did this, but with numbers in the previous problem for the linear velocity. And so this becomes, well, the final velocity or the final angular velocity is omega f minus 0 over a time interval of capital T. So now we just got to plug it all together. I times omega f over t. There we go, E. Very nice. We'll skip 26. That's about momentum and energy. Let's go ahead and look at we'll skip 25. Let's look at 26. Two projectiles are launched with the same initial speed from the same location, one at an angle of 30 degrees and the other at an angle of 60 degrees with the horizontal. They land at the same height at which they were launched. If the air resistance is negligible, how do the projectiles' respective maximum heights, 30 and 60 degrees, and the times in the air, T30 and T60, compare with each other? So here are our answer choices. And they are launched with the same initial speed. Give you guys about 10 seconds. I'm surprised this is actually a physics C question, to tell you the truth. It sounds intimidating. All righty, so what can we expect? Well, the more upright I shoot an arrow or a projectile, the higher it's gonna go, right? The physics explanation being that you have more and more vertical velocity. So we should expect that the height of 60 is gonna be greater than the height of 30 degrees. So that's going to leave us with either D or E. Now, what should we be thinking about the time? Well, the higher it goes, the more time it spends in the air. So the time for 60 should be greater than the time for 30. So bam, there we go. All righty. Let's go to 27. Ooh, this one looks interesting. Students are studying the motion of an object that is moving in the XY plane. The x and y components of the object's velocity Vx and Vy, respectively, as functions of time are represented by the graph shown above. Which of the following is a correct claim about the x and y components of the acceleration of the object and provides evidence to support this claim? Okay. All righty, so let's go ahead and take a look at this one. Students are studying the motion of an object that is moving in the XY plane. Oh wait, we already read the question. Rip. So let's see here. Well, what I like to do is I usually try to like answer the question to some extent on my own before looking at the answer choices. I don't know if that's like actually recommended, but you know, at least it kind of keeps us from just reacting on gut intuition on the answer choices, which sometimes have gotchas. So the acceleration here, which is the slope, is 0 initially. A is positive, so A is increasing. Now, the velocity of this object is slowing down. And so we might be thinking something about decreasing acceleration. But remember that, again, acceleration is a slope. And if I have a straight line, that line has a straight slope everywhere, it has a constant steepness. And the steepness tells us the acceleration. So the acceleration here is constant. Now let's see what it is. Which of these? Now, do they give us the actual directions for which way is positive or negative? We're going to go ahead and assume that because they're plotting them on the positive part of the graph, it's positive. So A of x is positive and A of y is 0. And components of the acceleration here, they're, wait, what? Why would they say this? Well, just because the acceleration here, hopefully we recognize is changing. I think this is a gotcha. They're hopefully thinking, oh, I see 0, so then I'm going to say 0. But no, this is velocity, and they're asking about acceleration. Because the final velocity of Vx is positive and the final velocity of Vy is 0. Wait, what? No. Remember, components in perpendicular directions do not affect each other, regardless of whatever the velocity in the x direction is. That is independent of the velocity in the y direction. There is no correlation between them, two independent dimensions. So A is like wrong on a couple of levels, in my opinion. Let's go ahead and look at B. AX is positive and increasing. Okay, this sounds better. AY is negative and constant. This is exactly what we were saying. Now let's hopefully find the best evidence to support the claim, because the slope of Vx is positive and increasing, and the slope of Vy is negative and constant. Okay, yeah, this sounds just like what we were looking for. Let's go ahead and just look at the other ones just in case. AX is positive and increasing. Okay, checks out. AY is negative and constant. Okay, sounds good. Because the values of Vx are positive and increasing. Ooh. Is this a select 2? No, there are no select 2s on AP Physics C. So this, I think, actually sounds a little better. Oh, okay. No, they say the same thing here. I just don't agree with the second part of C is all. Because the values of Vy are negative and decreasing. Actually, hold on. This reads a little confusing because here they're talking about the values. So because the values of Vx are positive and positive, okay, and increasing that, I actually agree with this part a little bit better. And then the values of Vy are negative and decreasing. The problem that I have with this is that this does not, oh wait, no. They don't address anything about why AY is constant. So again, it sounds really good, except for this part here. So I'm going to have to disagree with answer choice C. And so again, just to reiterate what they're saying, AY is negative and constant. Yes, I agree, and that is true. Now, the justification for this part says that the values of Vy are negative and they are decreasing. So Vy is positive right off the bat, so that's not true. But they are decreasing. But then again, they don't even explain why it's constant in the first place, which is better explained by the fact that we're talking about the slope in B. So C has a lot of little gotchas that sound good, but if once you start to dig into it, you recognize, wow, they're saying a couple of wrong things here, glaringly wrong. Okay, and things that are not true. All right, so AX is positive and decreasing. Okay, not true because the slope is increasing. AY is negative and decreasing. No, we said the acceleration is constant. So again, no. Okay, I think we get the gist for this question here. But if you want me to talk about E, let me know in the chat. All right. Here's another one that I think sounds familiar. A projectile is launched from the top of a 15 tall meter building at a speed of 25 meters per second at an angle of 50 degrees above horizontal. The horizontal distance from the base of the building to where the projectile lands is most nearly. So this one may require a little bit more time. Okay, so I think we'll go ahead and get started on answering this question. Ultimately, the horizontal distance depends on the horizontal velocity and the time that it is in the air for. Now, to get the horizontal velocity, that's going to become 25 meters per second, but then we need to get the horizontal component. When we launch this bad boy at an angle of 50 degrees, the horizontal component is V cosine theta. So that's going to be V cosine of 50 degrees. And sadly, they do not give us a nice number to work with. I kind of don't like that, but whatever. Oops, I have a double V. Let's just bring the lasso in to bring it in a little. Okay. But we'll go ahead and I think we can actually estimate this, because hopefully we know cosine is 60. And then times the time that it is in the air for. So who knows how long that is, but let's go ahead and see here. So cosine of 60 is about 0.5. It is 0.5, right? If anyone wants to check that for me, because sine of 30 is 0.5, so they're complements of the complementary angle. So they should be the same. So this is a little bit less than 0.5, so we should expect this velocity to be about a little bit less than 12, but we'll hold off on that. How are we going to get the time that it is in the air for? There are a couple of ways to do this. And maybe if you happen to have a calculator with a solve feature, it's probably best to just throw that bad boy into your calculator to solve. Where at the end of the day, what are we doing? Well, we have to talk about the time that's in the air in the vertical direction, because that's what's going to determine the time in the air for projectile in this case. It's not hitting a wall, so the horizontal motion isn't determining the time it moves. In this case, it's hitting the ground, which is a vertical displacement. So we have delta y is going to be v in I in the y times t plus 1/2 at squared. And if you notice, well, where's the at squared for this equation in the x direction? Remember that the acceleration in the horizontal direction for projectiles with no air resistance is 0 meters per second squared. So we ignore all that secondary part. Okay, so what are we doing? So here we can go ahead and start plugging in some numbers. This is going to be the vertical displacement. Now, yes, the ball is going to go up, but then it's going to return to this point. So at the end of the day, the displacement is only the part from the edge, the height of the building. So this is going to be 15 meters per second. I'm sorry, for 15 meters. Now, what do we do here with our directions? Well, we could say that it's down. So this is technically a negative. All right. And if we didn't have a velocity in the up direction or in an opposing direction, we would be fine. We could choose down to be positive. But here we're going to have to be a little more careful. We'll go ahead and say that because the projectile is inclined at 50 degrees above horizontal, it's going to have a vertical component pointing up. So this becomes 25 sine of 50 degrees equals, oh, sorry, not equals, plus 1/2 AT squared in the y direction. Okay, all righty. So, and I forgot a t, man, I am being real sloppy. I apologize for that. VIT, we don't know the time, plus 1/2. And on the AP exam, you can just use 10 for G t squared. There we go. And you could throw this into your calculator, which the syntax would be solve this expression for t, and then it's going to spit out a value for t. There's another way to do this, but I think it's a little bit more complicated in this case. You could find the vertical velocity. So, and the vertical velocity is not very easy to get unless you have a calculator here. But let's say, right, we did this in physics 1. Let's say it's launched at a velocity of 30 meters per second upward. If the vertical component is 30, it's going to take it 3 seconds to reach the peak because it loses its speed at 10 every second for the gravity. And then it would take it another 3 seconds to come back down. So far, if I had launched it at 30 meters per second upward, that would have spent 3 seconds going up, 3 seconds going down. And then from there, you could find the time that it takes it to fall down the rest of the 15 meters with a vertical velocity of 30 down. But that's still going to be more steps than this ultimately. So you could either solve this with the quadratic formula, which I think by now most of us have calculators that could throw this into the solver. So I'm going to assume that that's what we do. But if you want me to do it with a quadratic formula, let me know. In the meantime, I'm going to pull up Wolfram Alpha just to have it solve for me because I don't have a solver on me right now. And so give me 1 second. So we have negative 15 equals 25 sine of 50. And I'm going to use, we'll use T. We have a keyboard. And then, oops. I'm getting a little sloppy. The negative for the acceleration due to gravity because it's down. As I was typing it into the equation, I realized I had written it down as positive. But we are adding that term, but the acceleration is downward, which kind of forces our hand to say that because we shoot it upwards and we chose up as positive, you know the deal. Plus, and I'm going to go ahead and just put it as 5 t squared. Okay. So if you guys are curious about what Wolfram Alpha is saying, I can share that with y'all. Where is it? Here we go. Okay. So here is our quadratic expression. And at the end of the day, we get two solutions. One is 0.66707, but that's negative. That's this solution over here. So we don't want that one. We want the other solution, which is about 4.49. So at the end of the day, let's go back and screen share OneNote. So about 4.49. So T is 4.49 seconds approximately. Multiply that by 12-ish, because we said that this is approximately half of 25, which is about 12. So when we multiply this by about 12-ish, 4 times 12-ish is about 48. We'll go ahead and say that 43.8 is good enough. Oops, I just realized I paused the share. So what you missed during the share was that this right here, the velocity is approximately 12, and then times the time in the air. 12 times 4 is about 48. We are over rounding, so we could go ahead and recognize that the best answer choice here is C. Okay, so sorry, that was a long or a large amount of time spent on that question, but we'll go ahead and finish these out. So a person wants to paddle a canoe from point X to point Y, which is directly across a river from point X, as shown in the figure above. The water in the river flows at 5 meters per second, and the person can paddle the canoe at 10 meters per second in still water. Which of the following vectors best represents the appropriate heading of the canoe if it is to land at point Y? And they want best represents the heading of the canoe. Oof, this does not lend itself to screen share very easily, but again, we'll just redraw the figure here. I wonder, do I get the ruler? Oh, I did not get the ruler. This is point Y. This is point X. And so we know that we're going to have a velocity. We can row with a velocity of 10 forward. But the river is going to have a velocity of, I believe, 5 meters per second. 5 meters per second. So if I just row straight forward, my heading is going to be in this direction. Now let's see here if they want us to change anything. So which of the following vectors best represents the appropriate heading for the canoe if it is to land at point Y? So if I just do my normal heading like this, if I just paddle straight forward, the current's going to take me to a point behind point Y. So if anything, I need a row such that even though I'm going to be traveling slower overall, I'm going to travel against the current so that when I have my component of the velocity with the current, my horizontal component here should actually be 5. And that might be a better question. What angle should we head at to end up exactly at point Y? Well, because the river has a velocity of 5 meters per second this way to the right, we need a velocity of 5 meters per second to the left, and we are stuck rowing at 10 meters per second. Oh, well, if we notice, this is the opposite side. This is the hypotenuse. And when the opposite side is half of the hypotenuse, that corresponds to an angle of 30 degrees. So it turns out that if we row at 30 degrees from point Y, then we'll go ahead and land there. So which of these is that going to be? Well, definitely not A, not B, not C. Ooh, so I'm glad we kind of discussed this because this helps us determine right away which one is it. Well, this is a much larger angle than this, so I'm going to assume that this is closer to 30 and this is closer to 60. So, well, bam, there we go. Okay, let me know if you guys have questions, but I think you guys got it. All righty. Here's question 30. The graph shows the position as a function of time t for an object in linear motion. What they mean here is that even though the graph itself is not linear, the thing is only moving back and forth or whatever in a straight line. Which of the following graphs best represents the velocity of the object as a function of time? So I think this is definitely, I think, a new question to y'all. So hopefully you guys try to tackle this one, which I'm sure you've been doing all of these, right? You guys are exceptional students. So we have position as a function of time. Well, bad. Yo creo que ya llegó. Oh shit. Oops. Sorry. Okay, sorry. All right, we're good. Okay, so let's go ahead and see here how we're supposed to tackle this question. So we're looking for, they want the velocity. So again, we want the slope. But what is the slope look like here in this region? Well, by golly, the slope is constant. The slope's constant to right about here. So what this tells us is that V is constant. Okay, at some point, the velocity is 0. And the velocity is changing at a, if we notice here, we actually have a bit of a parabola. So this tells us that we're going to have some generally constant acceleration in this second portion here that I'm actually going to go ahead and highlight in red or magenta. So in this region, this looks like we have a parabola, constant acceleration, constant downward acceleration. So like a negative slope is what we should be expecting. So not only do we have a negative velocity, but we have a concave down function, which is the second derivative, which is the acceleration on a position graph. So we should expect a linearly changing velocity in this region after the second tick mark. So we're going to have a constant velocity and then a linearly changing velocity. So I don't think C works. Maybe A, B, or nah, not D. Maybe A, B, or D work. Let's go ahead and analyze it a little further. Well, we know that the velocity happens to be 0 at the third tick mark. So let's see here if any of these can help us fine tune it a little bit more. The velocity here is 0 at right before the first or second tick mark, sorry. So that tells us D is out. So it's one of these two. Okay. Well, we have a positive slope here. Which way are we moving? We're moving towards positive X values. So we should have a positive velocity. So, well, bam, there we go. We could have probably just started with that, and that first feature automatically defines it. But I kind of wanted to talk about the other features before just answering the question. Okay. 31. An object with an unknown initial velocity has a constant acceleration with components of 8 meters per second squared and 0 for the X and Y directions respectively. Which of the following is a possible expression for the position of this object in meters for both X and both the X and Y directions as a function of time? Okay. So as we've been saying before, acceleration is the second derivative of position with respect to time. And so there's a couple of ways to do this. We could go ahead and split our differential. And here we luck out. The acceleration is a constant value for X and a 0 value for Y. So we can just go ahead and throw this into an integral. So the velocity of X, when we first integrate it here, is going to be A of X dt, which is also equal to the integral of d to dx. I'm not going to worry about this. This is just like math formality, but we already kind of like said that's velocity. Okay, what do we do? So in the x direction, that's 8t for the velocity in the x direction. And then the velocity in the y direction is going to be 0 times t plus c. Oh yeah, plus c. Oh, they don't even worry about that. So there's no acceleration. So whatever velocity in the y direction, that's just that. Okay. So then we got to integrate this velocity again. So we integrate 8t dt from like 0 to t, bad math notation, but whatever. Here we're looking at the applications. So that becomes 8t squared over 2, and then plus like v naught t plus like x naught or whatever. But we don't have any of the initial conditions, so we're just going to ignore that. So it looks to me like this was kind of a gotcha here. Okay, maybe we were thinking, oh yeah, 8t squared right away. But remember, when you integrate, you got to divide by the power. So on the second integration, we're going to have to divide by a 2. So one of these two. And then if you notice here, which of the following is a possible expression for the position in both directions? So all we know is that the acceleration is 0. Remember that derivative information does not tell you anything about the value of that function. So even though I know the acceleration is 0, well, we don't know what the velocity is. We could be moving at a constant velocity. It could be 0. So maybe some people saw y would be 0, like there's no acceleration, the position never changes in the y direction, it's at 0. But we don't even know where it started in the y direction initially. So this is wrong on several levels. The one that works here, well, let's see here. We might be wondering which of these works better. Well, if we had an acceleration in the y direction, then we would have some kind of quadratic term for the position, but that's not the case. So then here, when we integrate Vy to get x, that's going to be the integral of 0t plus c dt. The 0 part is still 0. That, it's going to be like 0t squared over 2. Yeah, whatever, that's still 0. But then over here, we get plus c times t. And then plus like some new constant, which is the original position. And this constant here being like the initial velocity. So it looks to me like the better expression here is D. What we've done this I think this question has been done so many times, but just real quick, which of the following best indicates the direction of the acceleration if at any point at point Q? Straight down. All right. Even though the velocity is 0, the acceleration due to gravity is acting on it. So, and we assume, oh, well, now let's make sure that there's no air resistance. But I've seen this figure so many times, and it's just like, sadly, I know. But yeah, air friction is negligible. If air resistance was not negligible, we would have an acceleration in the x direction from the air. And so then therefore the acceleration at this point would be something like this. I think I'll keep that in mind for a test question later. Alrighty, I think this is the last one. Thank you for sticking by, really appreciate it. Let's go ahead and see here. The speed v of an automobile on a straight road is given in meters per second as a function of time in seconds by the following equation. 4 plus t cubed. How far has the automobile traveled in an interval between 0 and 2 seconds? Okay. So here the question is asking how far has it traveled? This is a distance traveled question. So we have to be careful because if we kind of just throw some math at this, we're going to be getting the displacement, which is not the same thing. So what is this math that I'm talking about? Well, to find out how far it has displaced, we would take, remember, and I'm kind of combining algebra notation with calculus notation. But we could start with the fact that dx dt is the velocity. And then we can split this up and say dx is v dt. And we can integrate both of these functions, or well, both of these sides. Dx is not really a function right now because it's just a differential change in position, a tiny change in position. We're going to add all those up from 0 to x final, wherever. That's the, and this would give us our displacement from wherever we went if we set the original position to be 0. The more interesting part here is the left or the right hand side, 0 to t, or 0 to 2. So we have to be careful here. We are going from the lower bound of 0 seconds to 2 seconds. But what this would give us, and we could even be a little more general on the left-hand side here. Sorry, I probably should have just done that and written it as x initial. Because x final minus x initial, that is our displacement. That's why I was jumping to that part of the equation. But that's going to be equal to this is the displacement, which is the integral of velocity with respect to time. So how do we turn this into a distance traveled? Well, the quick way is to take the absolute value of the velocity. So you know what? Let me finish this out as 0 to t and then write what I really want to do down here. So in reality, d traveled, because this is the problem. Hopefully you recognize this is a cubic. Probably this thing is doing some funky stuff at cube root of 2, because at cube root of 2, when t equals cube root of 2, that gets 2 times 2, that's 4. And if it's negative, then that's going to give us a velocity of 0. And for times beyond that, that might be slowing down. Here, I think we luck out. For every portion of time here, it starts out with a velocity 4t. It's just going to grow something like this. Because at 1, that's 1 cubed times 2, that's going to be 6, and then it's just going to keep growing. So here we don't have to worry about the velocity ever being negative. But if the velocity ever ended up being negative, like if this was 4 minus t cubed, then we would have to be careful with that, because that negative velocity would cancel displacement, but it would just add to our distance traveled. So here, this would be the absolute value of 4 plus 2t cubed. But because everything here is positive, we don't have to worry about any shenanigans. We're just going to integrate this monster from 0 to 2 seconds. So that becomes 4t plus 2t to the 4th over 4, evaluated from 0 to 2. And so this becomes 4 times 2 plus 2 to the 4th over 2. Sorry. And then minus a big old 0 for everything else. You may be wondering, why did I cut this in half? Well, 2 over 4, right? So what does this become? This becomes 8 plus 2 to the 4. That's 4 times 4. That's, wait, no, I don't think I did that right. I think I jumped ahead. Because 2 cubed is 8, right? So then, oh yeah, it is 16. I was splitting it as 2 squared times 2 squared, which is correct. And I just thought for a moment that was too small. 16 over 2, that's 8, 8, 16. Well, bam, there we go. Okay. So I do apologize. I do actually think we've gone over like 99% of these questions. Maybe one was new. Now they all sound really familiar. So I will definitely look for more questions, because I think that is kind of our time. But I hope we still got something out of it. Even if they did seem familiar, they reinforce some of the main ideas. But I will look deeper for different questions, because I think we've seen that kinematics is easy, but we can always do a little bit more with it. Any last questions, thoughts, concerns before we call it here?
No,
No,
I'm
sir.
good.
Yeah,
All righty. All right. Well, we'll catch you guys later. Have a good one.
thank you, sir.
Bye-bye.
Bye.
Bye, sir.
Bye-bye.